Great pleasure to invite Sourav Ghosh to speak on finite step rigidity.
Yeah, hi. Thank you for inviting me to give this talk. And thanks to the organizers for having this wonderful conference going on here. And a belated Happy New Year to everybody. So today I will talk about finite step rigidity, which essentially means that in certain cases, you don't have to check the full spectrum, but only a finite part of the spectrum would be enough to decide if two representations are conjugated to each other or not. And I'll define the special case where that happens and why that special case is also important in its own right. So let's start. So let gamma be a fundamental group of a compact orientable surface without boundary and of genus at least 2. So for me, it would be something like this. This genus is 3. And you want to consider its, and also you have this representation of PSL2R on PSLNR, inside PSLNR, called the irreducible representation. I mean, to give a sort of computational way, how does it act? This iota of the matrix A, B, C, D acting on these polynomials or monomials, this acts as x plus by to the n, x plus by to the n minus 1, cx plus dy, blah, 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 cx plus dy to the n. So this is the irreducible representation. And you consider them, and then you define any injective homomorphism from gamma inside PSL and R, which can be factored through this irreducible and a representation inside PSL2R. It's called a Fuchsian representation. Now, Hitchin in 1992, he showed that if you consider the representation variety and consider the connected components of the representation variety, and particularly those components which contain the Fuchsian representations, those connected components are topologically trivial, which means they're diffeomorphic to open balls. And his reasons were quite different from necessarily studying these representation things. His reasons were, I think, motivated by physics and solving Young-Mills equations under some symmetry conditions. And the moduli space of such solutions seems matched with this space of Hitchin representation or some such thing. So for us, the main goal of object are Hitchin representation. So what is a Hitchin representation? It's anything that is inside the Hitchin connected component. That means those connected components where the Fuchsian representations are there and which are topologically trivial. Any element there is called a Hitchin representation. Now, there was a question for a long time that can you geometrically characterize a representation inside that connected component without actually, like the definition of the representation is that something which can be deformed to a Fuchsian representation continuously. But is there any other characterization from just looking at the data of the representation or the lengths or whatever? Can you decide if the representation is Hitchin or not? And so this was like, so to give a characterization of such a nature, I have to introduce a few notions. So let's, so you have gamma be an element of that group and that boundary gamma be the Gromov boundary of the group gamma. Or in the case of the one that we are working here, you can think of it as the boundary of H2, the disk. You can think of this as the boundary of gamma, essentially. But one could give a like independent construction starting only from the group and only considering wards and defining distance on them. Right. And gamma, the action of gamma on the boundary of gamma has an attracting fixed point and a repelling fixed point. So in our pictures, it will be like something like if you have some hyperbolic element gamma, it will have some, it takes x to this gamma x. So this point is called gamma plus the boundary, and this point is called gamma minus. Sorry, gamma is an element of capital gamma, which was introduced in the previous slide, this capital gamma. The element small gamma is inside capital gamma, which is a surface group, in non-trivial element, sorry, in non-trivial element of, correct. And so what Laburi showed in 2006 is that if rho is a Hitchin representation, then for any non-identity element gamma inside gamma, the action of rho gamma on the flag space of, the space of all full flags of Rn, it has an attracting fixed point and also a repelling fixed point. I'll just define what a flag is, or like give a sort of rough picture. A full flag in Rn, so let's say F is equal to the tuple V1 up to Vn, where V1 is a subspace of V2 is a subspace Vn, which is equal to Rn, and dimension of Vi is equal to I. Such a thing, F is called a flag or a full flag, and flag space of Rn are all such flags. On the action of rho gamma on the flags have an attracting fixed point and a repelling fixed point. Yeah. So G, right. So the action is G of V1 blah blah Vn is G V1 blah blah G Vn. And okay, so from there, what it implies that, so if you take these points, this xi gamma plus and xi gamma minus, for each elements in the group gamma, you will have those things. Now you take sequences of elements for each element on the boundary. So using continuity argument, you will get a map which extends that xi map from the boundary of gamma to flag space of Rn, which is called a limit map. The definition in the paper is given in a bit different way. I mean, it says that if there exists a limit map which satisfies blah blah property, but this is a, in my understanding, more intuitive way of looking at the limit map. Now I'll introduce something called the hyperconvex maps. These are, again, will be needed for characterizing things. If you call a map F from the circle to Rpn minus 1, hyperconvex, if you take any n points on the boundary, any n points on the circle, and correspondingly you check this image of the map, then they should add up to Rn. I mean, it should be a direct sum. Is K is n, sorry, right, there's a typo here. K is n. That thing should add up to Rn. And take the projection map from the flag to the first coordinate. So pi of F is V1. This is the definition of pi. Then you have this, that the limit map xi, which comes from Fuchsian representations, that is a Veronese embedding of the circle inside Rpn minus 1 because of the exact formula that I've written here. And hence, pi compose xi is hyperconvex. There is something to be checked, but I'm not checking it. And so what the characterization was, Labouri showed in 2006 that if xi is a limit curve of H representation, then pi compose xi, in the first coordinate projection of the flag, is hyperconvex. And it was also shown by Guichard in 2008 that the other side is also true. If a representation admits a hyperconvex curve, then it has to come from the limit curve of H representation. And also the consequence of such results is that you sort of roughly have uniform eigenvalue gaps, which essentially means that if you take the ratio of the ith eigenvalue, modulus of the ith eigenvalue, and the modulus of the I plus 1th eigenvalue, where the eigenvalues have been ordered in this way, then you have sort of roughly, it increases in terms of gamma. For single elements, if you take powers, this is trivial. But the main point is when you multiply two elements gamma and theta, there's no guarantee that two diagonalizable elements multiplied will still be diagonalizable with distinct eigenvalues and things like that. So it's about the control of these kind of things. So now let's define the Benoit limit cone. So you take an element in PSLNR. I mean, it can be defined for any semi-simple Lie group. You take an element and you take its projection, take its different eigenvalues, take the modulus, and put it in a tuple. And you call this the Jordan Lyapunov projection, but I just wrote Jordan projection here. This can also be defined in a much more Lie theoretic way and not this kind of a, just you take the eigenvalues and stuff. I mean, you can, but I'm not giving the definition. And Benoit cone is, you take these, so for each element, so you take a representation of gamma inside PSLNR, and for each element, small gamma inside gamma, you consider inside this kind of a space, you will have, so for each gamma, you will have these kind of points inside the cone. And if you take the lines joining these points and the origin, then this object is called the Benoit cone, Benoit limit cone. So he proved, so in 1997, Professor Benoit proved that rho gamma is Zariski-dense in PSLNR if and only if this cone has non-empty interior. So that means in R3, if you have three coordinates for these eigenvalues, it should like fill up the whole thing. So now I come to a result from 2002 by François Dalbo and Inkang Kim. They show that if rho1 and rho2 are two representations inside PSLNR, any representations, and which have Zariski-dense image, and their Jordan projections match up for all gamma, then rho1 is conjugate to rho2. Similar kind of results without checking the full Jordan spectrum, but only checking the first eigenvalue and things like that, and only for simple geodesics and stuff has been done by Labouri, Canary, Bridgman, Sammarino, and also later by Labouri, Sammarino, Labouri, Bridgman, and Canary. But we will not go there. We'll just try to give a proof of this result using Benoit's technique, and I think Benoit's method. I mean, this was done by in their paper itself. You consider this rho1 gamma and rho2 gamma inside PSLNR cross PSLNR. Then from Benoit's result, we know that the limit cone Zariski density is if and only if the limit cone not having non-empty interior. So here, because there is this non-trivial relation between lambda rho1 gamma and lambda rho2 gamma, which essentially means that the Jordan projection of these guys will stay in a lower dimensional subspace. And so that would essentially mean that this group, the Zariski closure of this group is not the full group PSLNR cross PSLNR. And from there, a standard kind of, because it's a simple Lie group, using standard arguments, one can show that that they have to be conjugate to each other. So what we prove in recently is kind of a finite version of this object, this result, but where we do not assume Zariski density, and in place of any injective homomorphism, we assume that it's a Hitchin representation. So what we use is this beautiful result called escape from subvarieties lemma from a paper of, I'll say it. So let's S be a generating set of some group gamma in wherever, and consider BSN to be the wards coming from this generating set of length at most n. Then Eskin, Moses, O proved in 2005. I mean, it's a proposition in that in their paper using which they prove some other results. That if you have a if you have a Zariski, I mean the Zariski closure of some group inside GLNC, then any proper subvariety of G, the group will, there's a fixed number n after which the group should be outside that thing. It's kind of like in algebraic geometry, like circles are determined by 3 points. So if you have more than 3 points which are supposed to go through the circle, the only 3 is fine. It's kind of like that. So after some point, you don't need more data from the group. And I would like to thank my friend Chari for bringing this proposition to my notice. And this proposition, I use it in a key way to prove my results. So what I do in this archive article, which is yet to get published, so I construct explicit bounds for this nx that are there. And also using these things, I prove this result. So the statement is we take 2 representations of gamma inside PSLNR, which are Hitchin representations. Then there exists n, which only depends on this n, such that for any finite generating set S, rho1 is conjugate to rho2, whenever their Jordan projections match up for all gamma inside BSN. Now, there's a little bit of cheating here in the sense of that this capital N depends on n, correct? But also it depends on the choice that we are choosing working with Jordan projections. If you had taken some other functional equality here, it would also depend on that functional equality. But as long as we are checking only Jordan projections, this only depends on this n and nothing else, not the generating set. It's a ball of, so it's like you take the generating set, multiply n many of them, and then that's inside the ball. Yeah. I give a, so that's exactly what I wrote here. I give a, I mean, in the original paper, they had, all the arguments were there, but they didn't actually explicitly give a bound. But I give an explicit bound of that in this paper also. And right. So what's the proof idea? So essentially, the thing that we use is that Hitchin representations have distinct eigenvalues. It's a result from Laborie and Guichard, exactly the result that I stated before. And also the fact that PSLNR is a split group. And because of that reason, you don't have these complex numbers like this M group is not, it's a discrete group, which means you don't have bad complicacies that can appear because we are checking only modulus of the eigenvalue. If you had only eigenvalues, then you can take trace and it's an algebraic condition and there is nothing much there. But because it's modulus of the eigenvalue and you are not checking infinitely many, then there is something non-trivial that should come from the representation itself. You cannot expect such a result in general for any representations. We choose Hitchin representations, and there, so because this is split, and in this particular case, this is PSLNR. So just taking the squares do the job. You take the squares of these elements and take the trace, and then you get kind of an algebraic condition out of these results, and that from there you essentially show that because it's an algebraic condition, it's you get an algebraic variety, and you don't need more than finitely many points to determine that variety, and that finitely many points is predetermined in some sense by the variety itself. It's kind of a Bezout's theorem application. So yeah, thank you.
Are there any questions?
So in the beginning of your talk, you stated this theorem of Laborie,
right?
Which said that if you have this element gamma, it has a single attracting and repelling point on the flag variety. So in some sense, this is saying that this is like a very proximal element in this representation, and then this holds for the rows from the Hitchin. So do you know if there is a larger set of representations of irreducible representation where you can deduce the same thing that the.
So they say I think there are something called maximal representations, and there are something called positive representations. In both those settings, similar kind of stuff. But also, there's more generally Anosov representations, which are Anosov with respect to minimal parabolic. There also you expect that. So Laborie's main part was not just showing that you have such kind of a Schottky action or like this thing, but more the fact that the limit curve has to be of a very particular kind. Like this hyperconvexity is much more restrictive, which gives you the Hitchin component things. Otherwise, it can be in other components also. And I think a result by Barbo shows that you can have components where the eigenvalues are distinct and this kind of proximality is there, but it's not Hitchin.
Thanks.